So we're going to do the discussion section, and let me first start by opening it up and asking if people just have questions in general for the speakers that they would like to ask. No? Okay, so let me try asking sort of a general question to try to stimulate discussion. We heard about rods and inanimate things moving, self-propelling rods. On the other hand, we've also seen movies of real bacteria swimming, moving, or perhaps just growing and pushing others out of the way. The question is, how much do these have to do with each other? What are the differences? What are the similarities? What can we learn from rods that will tell us something interesting about bacteria? What can bacteria tell us about rods? So there are 4 questions right there. We have 6 people. That should work. You go first.
I mean, I think that was sort of one of the things I was hoping to get out of this conference is that it seems like with hydrodynamics, hydrodynamic interactions and sort of, say, maybe contact interactions, you get very similar patterns, but it seems like some things are different. And so is there some type of mapping that you can do to sort of say, like, hydrodynamics are effectively the same as in some situations as sort of these contact interactions? Because a lot of times you do get these same kind of patterns. So in that sense, is there some universality, or kind of are they different?
Hydrodynamics and contact interactions are inherently different just because of the long-range part of the hydrodynamic interaction. So if the long-range part exists, if you didn't have Gareth swimmer where the long-range part is killed by the symmetry, if you did have the long-range part, you have 2 different objects. You have to worry about the things you're worrying about. In the short-range case, it's not there. So theoretically, those 2 problems are very different. I wouldn't imagine mapping them onto each other. But as far as pictures go, I'm not so sure how to say 2 pictures are similar. I mean, in terms of the patterns, that I'm not so sure.
The 2 pictures being the rods and the bacteria.
Yeah, swarming patterns.
Like if you get swirling patterns that are generated by sort of contact interactions, or swirling patterns generated by hydrodynamic interactions.
I don't know how to quantitatively look at it and see what's different or what's the same. Yeah, I do agree they look similar, but I've still not gotten a handle over how similar or how different.
Question? Yeah.
I guess in both the simulations and experiments, the system is either all self-propelled particles or all particles look the same, but they're not self-propelled. So is there some, what if you put a dead bacteria in the system of dividing ones, or if you make only some of the pneumatic particles self-propelled, is there some critical density where they can, take over the motion and get non-diffusive convective kinds of things, or do you have to have all one population or all another?
So I don't know the answer to the question, but people have looked at putting passive spherical particles in baths of self-propelled rod-like particles, right? Ming who has experiments with the beads in them and things like that. And there she finds a critical concentration beyond which something drastic happens. Critical concentration of active particles, namely bacteria, beyond which something drastic happens. The beads start moving very fast. But beyond that, I don't think that's a question that has been asked systematically, either experimentally or simulations.
I think in what's sort of been done so far, the, say, non-active things have been more as like a probe and don't have very much effect on the system as a whole. Whereas you make it larger or, say, more highly packed, I would imagine there would be some critical sort of amount. But I don't think any of that's been done so far. It's been more as a probe. So like if you only have sort of one bacteria in a whole sea of colloids or something it might behave more like a passive colloidal suspension, right? Especially if it's sort of densely packed.
So what is it? Lots of passive particles, few active particles?
Yeah, that may be different because you have, because if the passive particles have also sort of a big impact, say if on like the rheology or something, then the passive part might be a small effect. But if you're putting only a few sort of passive things into sort of as probes, then the whole concept behind that is hopefully it's not affecting what would be there without it.
Well, on a related note, it's kind of interesting because you discuss those two extremes, but and Paul asked, is there a critical size? And I guess, or a critical density of passive particles above which, say, or below which, whatever, you get predominantly driven versus predominantly passive behavior. But a big parameter in lots of theories of self-propelled particles is the noise level. Unfortunately, none of us know how to measure the noise level, experimentally. But I wonder if a passive particle could be a probe somehow to quantify the level of driving noise that and it maybe you can imagine. Because that's one problem with everything I do is I don't know what the noise level is.
Can you quantify your noise level? What's the definition of your noise level?
I don't know. I mean, it's a white force, right?
Is it like Brownian motion? Because if it's a Brownian motion,
it's a delta correlated force. That its spectrum is flat. But its amplitude, I don't know how to quantify in a bunch of self-driven particles, like in a movie.
It just amplifies noise. So what you're measuring is not necessarily the input noise; it's just the output of the system. So in that sense.
But perhaps the amplitude of fluctuations of a passive particle be a measure of that white noise amplitude.
That go back to the problems that you at one point, like rheology, that your passive particles are coupled differently.
Yeah.
I mean, how do the bacteria know? You talked about interaction between your rods, but how do the bacteria know there's another bacteria near it? I mean, do they have to hit it? Or is it just hydrodynamics? Or do they have some little sillier feelers out there?
I just was going to say, answering your first question, it depends on the density, I think, to a large degree. If the bacteria are far away from each other, then their interaction is more sort of active and chemotaxis or hydrodynamics or whatnot. And if the density becomes very high, like in my experiments that I showed or in the last talk, then they start to behave more like granular rods, and it's more generic kind of behavior, I would say. And for example, with this poster over there, and there were some experiments on microtubules when they start moving on the glass plate due to molecular motors. It's drastically similar to that swarming motion of bacteria. And again, because of the physics of just moving and colliding and sort of following tracks, this becomes more generic at high density.
But, I just want to go back to previous point. I mean, I think the swirling motion indeed is observed quite generically, whether you have hardcore in real systems and in models, whether you have hardcore interaction or hydrodynamic interaction and so on. But many other properties seem to be quite different. For instance, hydrodynamic interaction can produce a number of instabilities in isotropic states that short-range interaction not give you.
Well, that's what I'm saying. If the density becomes high, then it's hydrodynamics become less important than.
That's right. But, so I mean, there are some important differences. I think the swirling motion you see it everywhere, but it's not clear how it doesn't help you distinguish. I think so much different type of systems because it seems to be there all the time. That's why also I think it's certainly important to try to look theoretically and try to be able to understand what can you get with specific physical interaction, right, to disentangle them from the object. Now, going back a minute to what Paul raised, I think another question that I I wonder if one could look at that. I have no idea. I mean, we seem to find that there should be some observable differences between patterns observed and behavior of what we call puller versus pushers. That is, whether it's, say, things like Nicolai or Pseudomonas. What if you had a mixture? I don't know. I mean, what would be the behavior of a system where there are some of one type and some of the other? I don't know whether one could do that.
From a simulation standpoint, we have put mixtures of pushers and pullers. And we haven't done sort of the total sort of mapping the extreme from one to the other. But it does seem that it's not sort of a linear relationship, right? It's you can't take sort of a pusher and a puller simulation or theory and sort of if you're halfway in between, it's not going to be halfway in between the two. It's much more complicated, which considering the sort of large multi-body interactions you have, it's definitely a nonlinear problem. So probably wouldn't expect to see that, but I think there is sort of a lot going on there. I think experimentally it's pretty difficult to do pullers. So if anyone's a really good experimentalist out there and wants to tackle that, that would be great because Chlamydomonas is a little more difficult because there are a lot of other things going on. For example, we heard about in the soundbite its interaction with the light, and it's also heavier than sort of water, and it's also not uniformly heavy. It has a gravitational torque on it, so it's much more complicated to do experiments.
What about these acting filaments that I saw posted? Oh yeah. Are the acting filaments pull or push? I would tend to think if you stretch it, it likes to pull. So
actually,
maybe it's a good model for puller.
I actually thought about it when I had the preprint of Aparna's paper on the pushes and pullers, and I also came to the conclusion that this could be pullers in fact.
Why don't you use this?
So that would be a good...
Say that again, because you kind of speak in softly.
Okay, I was wondering about this question, whether those acting filaments are pushes or pullers. I was wondering about this question too, especially when I got Aparna's preprint about this pushes and pullers thing. She presented today, and I came to the conclusion that when you want to classify those actin filaments in terms of pushes or pullers, then these actin filaments for the molecular modus must rather be pullers.
That's a good model system because you said you can cut it in whatever length you want, right? So if we could get like fixed, say 10 micron length acting filaments and put them in a solution, and well, there are a lot of experiments one can do to figure out whether the prediction of tracking to the boundary and whether they are perpendicular to the boundary or... So suppose if you're putting a microfluidic channel, you can look at whether they are...
And actually we are working on well-defined boundary conditions by patterning the motility assay experiment with pacifying proteins so that we have modal proteins in a distinct region and no modal proteins in another region, so we have really well-defined boundary conditions. That's actually on the agenda.
Well, I kind of understand when I have an active and motor solution that kind of becomes contractile, the system. But how do I think about it in the motility assay context? How is it a force that, I mean, how does it look like a puller in a motility assay context when the motors are out and the actin is sitting on top? Now I'm just asking for your thought process behind that. How did you think that it was a puller?
I don't think that this motor assay experiment fits well in this definition of pullers and pushes, but when I first looked at your preprint, then I thought this must be pullers because they are propelled by the molecular motors, and well, they leave behind the molecular motors, so to say.
Okay.
Doesn't the pullers versus Spencer's classification have to do with its hydrodynamic properties. It's using liquid to propel itself forward, fluid. But in this case, it's not.
Yeah, as I said, it doesn't fit too good in this pushes of
It's not.
But it will still leave a far field disturbance of some sort in this solution. But I'm not able to imagine in my head what that would be.
How does that compare with polymer? If you just have a polymer string, because that is a polar example. That's what we use as a polar example in our paper, down coat paper. So how does your actin filament?
Actually, I don't know about. I'm sorry, I don't know your work. So, are those polymers somehow propelled, or are these?
No, they're just passive polymers.
So why is a polymer a puller?
Because if you stretch it, it pulls.
Okay.
But how do you
The rubber band effect. Okay.
Right. So if you have fluid.
I don't know if that matches the hydrodynamic definition. My idea of puller is like the breaststroke. Am I wrong?
I would think the puller is more like a butterfly in terms of what it's doing. You pull fluid in at your head, not push fluid out.
Okay, you want me to know like this? Okay.
If we wanted to think inertial swimming, I would think it's butterfly.
Okay. Other questions or comments? One question I had was, we heard that thing about swarming and flocking, and someone said, oh, well, bacteria don't do that. They're just kind of grubbing around for food. But if you mix together, going back to Paul's thing, some little rods, self-propelled rods, a small but finite concentration in a bunch of bacteria, could you get the bacteria to do something different if they weren't starving or not?
What was the question?
So the question was whether you could. This is the sort of flakiest microphone. I was just sort of random association, but we heard the talk yesterday by Owen about how you put in a few leaders right in the flock of geese. Just a few know where they want to go, and they make the whole flock go that way. So the question was, and then Paul was saying, well, okay, suppose I put a dead bacteria in a bunch of rods or something. Suppose I put a bunch of self-propelled rods that have a mission in mind among bacteria. Is that going to make the bacteria do something different if they're not starving and they're looking for food? Can you persuade them to do something?
If I were to take a guess, I would say nothing will happen. The bacteria will still do whatever they do. But that's just a guess, given the fact that hydrodynamic interactions mix, and I don't imagine the bacteria are actually
But that's the point.
deciding.
If you're generating a hydrodynamic interaction, well, then others follow because of that.
It's not aligning, that's what I'm saying. The hydrodynamic interaction is not something that aligns. So if you put a few guys that go in some direction, I don't think it will make the other guys go in that direction. The hydrodynamic interaction doesn't have that property.
But excluded volume.
Excluded volume does.
Yeah, that makes sense. Any other questions or comments? Yeah, go ahead.
Has anybody thought about looking for some statistic to pick up swirls?
Somewhat.
Like a statistic or something you can apply to pick up swirls in data. But
Well, what we did,
we don't know a center to do that.
some earlier work we did on swirls in granular rods, which we did with Aviva Shard and some other work. We just basically measured the cross correlation function between the velocity fields, and we had some correlations between velocity in two different dimensions, and that can be interpreted as with a certain ratio as a signature of rotating motion. But
So that's, in what I was doing, the reason I was calculating the velocity correlation function is that, right, you have a swirl and you go a distance where now the swirl is going in the opposite direction. You'd like to get a negative correlation, right? And in the sort of 3D periodic simulations I showed, you don't see any sort of negative, effectively you don't see any negative correlations. So you don't have any swirls. In a confined system, in our simulations, which I didn't show, you do get swirling patterns.
2D.
So it's it's 3D in a confined between two walls, and there you do get swirling patterns. I might just say, because this is a confusing thing, I see in the literature, is that if you have sort of hydrodynamically, if you're pushing sort of through the fluid in a confined between two walls, you get a swirl, right? Because the fluid is trying to, so you're pushing through a fluid and it tries to sort of move, and it tries to go up, say, or down through the walls, and it can't. So it has to go to the side. And so in our simulation, so what I showed today, I always compared sort of a non-collective behavior situation. If you look in sort of with walls, with boundaries, even in the non-collective behavior, you get swirling patterns. So I think people have to be careful. If hydrodynamics are important, if there are hydrodynamic interactions in walls, you have to be careful of saying a swirl means that you have collective behavior.
Even you can come by particles not talking to each other, but they're in the presence of the wall.
Exactly. So there are experiments in bacteria that see these swirling patterns, and the size of the swirl is bigger than an organism. But actually there was a wall sort of that distance away, and that's what sets the size of the swirl.
That's the characteristic of those types of swirls, though, right? Is they're set by the distance from the boundary, whereas other types of swirls have a different length scale. Vortices have a different length scale if they're not formed by the boundaries. It's a diagnostic of telling the difference.
Yes.
Which is important. It's a very important point. Like in chick embryos, for example, there's this vortex formation. And the question is whether that's set by the boundaries or not as well.
Yes, so I think when you're looking at some of these sort of collective behavior of groups of things, if they're interacting hydrodynamically and there are walls nearby, you have to be careful about sort of identifying a swirl as being evidence of collective behavior.
Which way would the swirl go? Is it if I have the wall here, is the swirl this way or is it this way?
Depends.
I just wanted to know if it was this way or
It's this way.
it's this
right?
way.
So the idea is that if you're pushing through a fluid and you're trying to, say, push the fluid up and down ahead of you, but it can't, so it has to go to the side. So it's sort of,
But the wall's underneath. Why is it going to the side?
because it can't go down.
Right,
So
so
it
then
has
it
to-
should go up.
Well, there's a wall on top as well.
Right,
If there's
so
a
then I
wall
should have
on top.
swirls this way, right? But he's telling me I would have swirls
But
parallel
if
to
the
the wall.
layer is very thin, then this motion will be done because of the higher.
Right, so you're saying that all the motion
This is
would
a
be...
larger scale motion, so it's more energetically preferable.
Okay. Is that the way it goes in a chick egg?
Luckily, in the chick egg, the walls are rounded. So it's around. So it's around.
Okay.
It's around. Yeah.
Right. Are there other questions or things people can think of? Those of you who still have the energy to think. I'd like to thank you all for staying to the end, and I'd like to thank once again the speakers for their talks this afternoon. Thank you.